You probably remember that experiment from school, pushing a strip of copper and a strip of zinc into a lemon and watching a tiny clock flicker to life. Electricity from fruit. It felt almost like a magic trick.
Now imagine this. What if your garden's soil works the same way? What if the ground beneath your feet is, in a sense, one enormous natural battery, and all it takes is two pieces of metal to tap into it?
Back in the 1840s, the inventor of the electric clock, Alexander Bain, explored that very idea. Using nothing more than copper, zinc, and damp earth, he generated electricity straight from the soil. His system powered machinery and, according to some accounts, even seemed to influence plant growth. Then, quietly, the idea slipped out of view.
Today, almost no one talks about the Earth battery. What happened to it? And if it worked then, could it still have a place in the way we grow food today? The story starts in 1841, when Bain, a Scottish clockmaker, filed a patent that challenged the way people thought about power. Instead of using expensive chemical batteries filled with acid, he buried two metal plates, one zinc, one copper, in moist soil and connected them with a wire. That simple setup produced a steady electric current drawn directly from the chemistry of the ground. This wasn't just a clever demonstration. Bain used his earth-powered system to run some of the earliest electric clocks. Their pendulums swung using energy pulled from the soil itself. His British patent number 8763 described how two different metals in damp earth could drive gears and electromagnets without winding, refilling, or replacing chemicals. The earth became the battery.
And the idea didn't stop there. As telegraph lines spread across Victorian Britain, the need for reliable, long-distance power grew. Bain's buried copper and zinc plates found a practical role in this expanding network. Telegraph stations adopted earth batteries to send signals along single-wire lines, using the soil as the return path, an approach inspired by earlier work in Germany.
Along railway routes, including the line between Edinburgh and Glasgow, these buried plates generated a low but steady voltage, often around 1 volt per cell, enough to power telegraph markers efficiently. Engineers even found ways to improve output by aligning the plates north to south and placing the zinc slightly deeper in the ground. Moist soil delivered the best results. Dry conditions weakened the current.
But when the soil stayed damp, the system could run for months with little maintenance.
Bain's notes and patent filings from the early 1840s reveal a technology that was remarkably simple and quietly powerful. Electricity harvested from soil chemistry using little more than scrap metal and water.
Other inventors built on the concept. In the late 19th century, American patents from figures like Daniel Drawbaugh and George Deal described linking multiple earth batteries together to increase voltage for clocks and telegraph systems. The principle never changed: two different metals, moist soil, and a complete circuit. In a world without centralized power grids, this was groundbreaking. Yet it remained largely unseen. Earth batteries worked silently behind walls and beneath railway embankments, proving that usable energy was already present in the ground.
Then people began noticing something unexpected. Telegraph workers and nearby farmers observed subtle changes in the soil around buried plates. In damp fields where copper and zinc lay underground, strips of grass often appeared darker, thicker, and taller than the surrounding areas. No fertilizer had been added, no compost spread, just metal plates and a faint electrical current passing through the earth.
There were no formal research papers at the time. The stories spread informally. A station master in Yorkshire pointed out a particularly lush stretch of grass running alongside a telegraph return line. A groundskeeper in Essex joked that the lawn seemed to know exactly where the wires were buried. Again and again, the same pattern appeared. Wherever the soil carried a steady electrical current, nearby plants seemed to grow with unusual vigor. Years later, a Connecticut doctor named George Starr White became fascinated by those strange reports from fields and telegraph lines. He was deeply interested in invisible forces, magnetism, electricity, the subtle energies most people never think about. To White, the idea that soil itself carried electrical currents wasn't far-fetched. He believed those natural currents might hold untapped potential for agriculture. In the early 1900s, he began speaking publicly about what he called soil electricity. Through lectures and pamphlets, he described experiments in which weak electrical currents were introduced into worn-out fields. In some cases, crops appeared to respond with renewed vigor. To White, electricity wasn't just something that powered machines, it was a natural force already present in the earth, one that plants might be quietly responding to all along. He made bold claims, but he stopped short of promising miracles. The evidence he collected was patchy and anecdotal. A strip of corn that looked greener, a row of beans that ripened a few days earlier than the rest. He presented observations and possibilities, not dramatic guarantees. Newspapers occasionally picked up these stories, though usually as curiosities. A 1915 agricultural journal mentioned a farmer who was convinced his potatoes grew larger near a buried wire. A Midwest clipping described grapevines thriving beside an old telegraph pole. Again and again, the theme repeated itself. No formal trials, no official backing, just persistent hints that something electrical in the soil might be influencing plant growth. To skeptics, it sounded like rural folklore. To experimenters like White, it felt like a missing piece of the puzzle, a subtle interaction between electricity and living roots that science had not yet fully explored. The question lingered in the background. Was the earth quietly nourishing plants in ways we didn't yet understand, or were these patterns simply coincidence? To move beyond speculation, the mechanism itself needed to be understood. When copper and zinc are placed in moist soil, they don't just sit there. Together, they create a small but measurable electrical reaction, effectively turning the ground into a natural circuit. This phenomenon is known as galvanic action. Here's how it works. Zinc, being the more reactive metal, begins to lose electrons. Those electrons travel through a wire toward the copper plate. At the same time, the moist soil, filled with water, dissolved minerals, and salts, allows charged ions to move between the two metals. This movement completes the circuit and creates a steady flow of direct current, the same type of current that once powered early electric clocks and telegraphs. But underground, that current may influence more than just wires. On a microscopic level, the zinc acts as the anode, slowly releasing electrons and dissolving into the soil as zinc ions. The copper acts as the cathode, receiving electrons and completing the reaction. Moisture is essential. Without water in the soil, ions cannot move freely, and the electrical flow weakens or stops. In damp, slightly acidic soil, the voltage between copper and zinc typically ranges from about 0.8 to 1.1 volts. That may not sound like much, but even a small electrical field can create subtle chemical changes underground.
This steady current can affect how nutrients behave. Compounds containing phosphorus, calcium, and potassium may shift under the influence of the electric field. The process resembles electrolysis, where electrical energy encourages ions to move and separate. Nutrients that were previously locked in stable forms can become more mobile and potentially easier for roots to absorb.
And roots, as it turns out, are far more responsive than we once thought. Plant physiology research has shown that roots react to electrical gradients, a behavior known as electrotropism. In controlled laboratory experiments, roots have been observed bending and growing toward the cathode, the copper side, when exposed to small voltage differences. Some studies suggest that roots can detect electrical fields as weak as 1 millivolt per centimeter. In other words, plants may not just passively sit in the soil, they may be sensing subtle electrical cues and responding to them. In a home garden, the electrical field created by an earth battery is gentle, almost whisper quiet. But even a small voltage, somewhere between half a volt and 1 volt across a short distance, falls within the same range scientists use in laboratory studies. In simple terms, two things may be happening at once. First, nutrients in the soil can become more mobile under the influence of that electric field. Second, plant roots may subtly grow toward the zone where those nutrients are easiest to access. The current can also nudge the soil environment in other ways. It may slightly shift the pH near each metal and influence microbial activity in the immediate area. Gardeners who have experimented with this setup often confirm the voltage with a basic multimeter. Even when nothing looks different above ground, the meter shows that something measurable is happening below the surface. The mechanics are surprisingly simple. 2 different metals, moist soil, and a connecting wire. Yet the idea behind it is compelling. With copper and zinc interacting quietly underground, the soil is no longer just a passive growing medium. It becomes part of an active system, subtly shaping how nutrients move and how roots respond. But by the early 20th century, this quiet electrical curiosity faced serious competition. A new force was reshaping agriculture, synthetic fertilizer, and it would transform farming on a global scale. In 1909, Fritz Haber and Carl Bosch solved a problem that had challenged chemists for decades: how to capture nitrogen from the air and convert it into ammonia on an industrial scale. By 1913, the first Haber-Bosch plant was up and running in Germany. Soon, affordable nitrogen fertilizer began spreading across Europe and North America. What once required years of careful crop rotation or large amounts of manure could now be achieved with a bag of manufactured granules. But this wasn't just about nutrients. It marked a shift in mindset. Advertisements in the 1920s and 1930s promised bigger harvests with less effort. Government agricultural bulletins, including those from agencies like the USDA, promoted NPK, nitrogen, phosphorus, and potassium, as the essential formula for modern farming. The message was powerful and straightforward. Soil fertility didn't need to be patiently built. It could be purchased, applied, and repeated. For farmers facing growing demand and competitive markets, the appeal was undeniable. Synthetic fertilizers were reliable, measurable, and predictable. Most importantly, they were consumable. Each season required another purchase. Economically, that model made sense. An earth battery required 2 pieces of metal and some wire, a one-time installation. A bag of nitrate or phosphate, however, guaranteed repeat business year after year. The change wasn't just technical, it was cultural.
Farming journals from the 1930s celebrated chemical brands with glowing testimonials and dramatic side-by-side photos of tall corn and lush wheat. Meanwhile, the quieter experiments with buried metal plates and soil electricity slipped into the margins.
By the late 1920s, some official bulletins dismissed electroculture as little more than a novelty. Research into soil-based electrical currents gave way to standardized formulas, chemical analysis, and yield statistics.
There's no clear evidence of a deliberate effort to suppress the Earth battery. What the historical record suggests is simpler. Markets tend to favor products that must be replenished, not systems that last indefinitely. As chemical production expanded and agricultural policy aligned around fertilizers, the Earth battery faded, not through conspiracy, but through economics and momentum.
The soft electrical hum beneath the soil, once a symbol of Victorian ingenuity, became easy to overlook in the era of industrial ammonia. Yet the chemistry itself never vanished. Whenever two dissimilar metals sit in moist soil, the reaction still occurs. The real question today isn't whether the phenomenon exists. It does. The question is whether it has practical value in a world built on repeat purchases and packaged inputs. That answer may not come from old archives, but from new experiments. Imagine a backyard gardener testing the concept for himself. He plants 2 rows of lettuce. In one row, he buries a piece of copper pipe and a galvanized nail, connecting them with a wire above the soil. The second row is left completely untouched, no metal, no added circuit. After 4 weeks, the change is hard to ignore. The lettuce connected to the buried metal stands taller, its leaves wider, and a noticeably deeper shade of green. When weighed on a digital scale, the difference becomes even clearer, an average of 38 grams per plant in the electrified row compared to 26 grams in the untreated row, close to a 50% increase. Curious, the gardener checks the setup with a multimeter. The display steadies at 1.03 volts, right within the commonly reported range of 0.8 to 1.1 volts, depending on soil moisture and pH. His growth notes show that the electrified plants began pulling ahead by the second week and never gave up the lead. He keeps careful records: soil pH, rainfall, voltage readings. At harvest, a simple statistical test returns a p-value of 0.04, just below the usual cutoff for scientific significance. Does that mean the system will double growth every time? No, but it does suggest something measurable is happening. The current in the soil isn't imaginary. Under the right conditions, it may influence how plants grow. And setting up the experiment is surprisingly simple. To turn your garden into a small living battery, you only need a few basic materials. Start with a piece of copper pipe or thick copper wire about 6 to 8 inches long. For the second metal, use a galvanized nail or a strip of zinc of similar size. These 2 metals are the heart of the system. You'll also need insulated wire long enough to connect the 2 metals, leaving a bit of slack so the connection stays above ground. Push the copper into the soil on one side of your plant's root zone, about 6 inches deep. Insert the zinc or galvanized nail on the opposite side at the same depth, spacing them roughly 8 to 12 inches apart. Moist soil is important. Dry ground weakens the electrical effect quickly. Strip the ends of the insulated wire and wrap one end tightly around the copper and the other around the zinc. Keep the connection above the soil surface so you can check for corrosion over time. That completes the circuit. Once installed, test it with a multimeter. Place one probe on the copper and the other on the zinc. In damp, slightly acidic soil, you should see a reading between 0.8 and 1.1 volts. For a proper experiment, log your voltage and soil moisture every few days. If the zinc corrodes heavily, replace it to keep the system working efficiently. With this straightforward setup, you can track plant performance through the season and see what happens in your own soil. Even now, a simple copper and zinc pair can draw measurable voltage from backyard earth. No special permission is required. No proprietary system is needed. While industrial agriculture relies on increasing external inputs, this quiet reaction continues beneath our feet, available to anyone willing to test it. The science can be measured. The scale is up to you. Sometimes the most powerful current isn't the one that comes from the grid, it's the one we choose to reconnect. If you decide to try it, keep notes, compare results, and share what you discover.